Last lecture for signals and systems is going to be on Z transform. The goal is to do many things, but we'll see how many we will be able to tackle. The least I want to do is maybe try to get to stability of systems, discrete LTI systems, just as we did for Laplace. Remember, what did you say about stability? The poles have to be in my left half of the plane. That's what tells me that it is a stable system. And depending on whether they are on the j omega axis, or they are in the complex plane, or on the real axis, I can talk about marginal stability, under-damped system, over-damped system, critically damped system. Those kind of things I should be able to comment about depending on where the poles are located, or how does the time domain signal look like in the case of Z. But in general, think of Z transform as Laplace transform for discrete signals. So, sorry, that's not an accurate way of saying it, but that's one way of thinking about it. So we'll talk about Z transform definition, formula. We'll try to apply that to a certain few discrete sequences. We'll talk about properties. We'll talk about discrete time LTI systems, computing the response of that, and then stability. And then if you have time left, which I don't think we will, we'll get to solving difference equations. If I'm not covering the topic, you will not be held accountable for that for final exam. Z transform. What is the definition? For Laplace transform, we said take the signal, put it through an integral, you have x of t e to the minus st dt. Similarly, for the discrete time, for a discrete time signal or a discrete sequence x of n, its Z transform or its frequency content is going to be cap x of z, which is now a summation. In here, we are doing a summation over all n, x of n, z to the minus n, where z is belonging to a set of complex numbers. Z belongs to a set of complex numbers, and I'm going to use a polar coordinate system to indicate this, r e to the j omega. Now, why am I using a polar coordinate system where in the Laplace domain, I used a rectangular system, right? I said left half of plane, right half of plane. Over here, I'm using polar. Why is that? The reason is the region of convergence for Laplace, what was it? It was never bounded in the vertical direction, but it was always bounded by something horizontal, right? Maybe a vertical strip, or maybe to the left, or maybe to the right, or everywhere. Now what you are going to see for Z transform is that it will be circles that will define the boundaries. So I want you to picture this. I want you to take the j omega axis, right? So this is sigma, this is j omega, right? Try to collapse that j omega axis onto the real axis like that, right? So whatever was in the left half of the plane will be inside the circle, right? So if the poles are inside the circle, you are stable. If the poles are outside the circle, then you are unstable. Things like that. So it's simply collapsing it. And what helps is polar coordinate system because of those circles being region of convergence. We'll actually prove this. Where does this come from? Can anybody tell me where did such a thing come from for Laplace? We had something like this for Laplace, right? What did we have for Laplace? Let me just write it down over here. For Laplace, we said x of s equals integration x of t e minus st dt, right? Where did we get this from? What's that? Orthogonal set, so that's why we picked exponential. But we got this by using convolution, right? So if the input is e to the st, what is the output? Well, the output for an e to the st system is going to be h, but h of s multiplied by e to the st, right? Eigenfunction is going to be e to the st, and the other piece, the eigenvalue, is going to be h of s, the Laplace transform of the transfer function of representing the transfer function of the system. So we got, based on that same criteria, that e to the st is an eigenfunction to that LTI system, while the eigenvalues are h of s's, and we'll prove this. Similarly, for discrete, you get z to the negative n, or z to the n, as eigen functions with the eigenvalue h of z, the Z transform of h of n, the impulse response of the discrete time sequence. We'll try to prove that. But that's where we are getting that relationship for. So once you, so give me the time sequence and I will tell you what that z is, x of z is. Very straightforward, right? Just plug it through this equation and you find it. What is the notation? Very similar to the ones, the time versus frequency notation that you have been seeing so far. X of n, z transform, x of z, cap x of z. And it's in pairs. So you go here, z transform. You go here, you're taking inverse z transform. Now, let's do a quick example here. X of n is given to me as this finite time sequence, and there's an underline there. What does that underline correspond to? We have already started preparing for final exam, right? The n equals 0, right? That's when n is 0. Next, I've given the sequence. I just need to put it in the x of z form. So let's try to do that. X of z. All right. Until this particular 0, I don't need to worry about that. From here on, I will use the values. So let me also put this. This one is -1, -2, and then 1, 2. That's it. So I've got x of -2 multiplied by z squared. Yeah. Plus 2 z1 plus 3 z0 plus 1 z -1 plus 2 plus 1 again 1 z squared. You see this? Oh yes, -2 there. Everything else is okay. 2 1 0 1 2 -1 -2 sorry -1 2 3 1 1. Yes. So we found the z transform, but what does Laplace transform contain? The function and the ROC. So x of z will contain the function and the ROC. So tell me the ROC here. ROC, region of convergence. What can z be and what it can be? It can be anything, set of complex numbers, but I have to subtract a 0. In fact, I also have to subtract plus and minus infinity from it. Because of 1 over z, right? I have a 1 over z here. And when I have a 1 over z squared here, because of that, I need to subtract a 0 from there. And because of these guys, I need to subtract plus and minus infinity from there. So z can be anything in the complex plane, any r e to the j omega, except for 0 and plus and minus infinity. Good. R is, yeah, exactly, right? Because it's the distance away from the origin. So within the circle, outside the circle, it's all controlled by r. Absolutely. Because omega here not affecting the magnitude. All right, next. We'll do that same thing for this guy. The problem is already done, so we'll just walk through it. X of n is a finite duration sequence, 2 raised to n, between 0 and 10. So it's going 1, 2, 4, so on up to 1, 0, 2, 4, right? So when n is 10, the value is 1, 0, 2, 4. And everywhere else, it is a 0. So this is a finite duration, discrete time signal. What is x of z going to be? Exactly the same way as we did before. We will take each value of x of n and multiply with increasing powers of z, right? So like we did z to the -2, we did z to the +2, +1, -2. So z power was actually decreasing as we increased n. That's what we are going to do for this. So we have 2 raised to 0, z -1, z -2, so on up to z -10. They are all getting multiplied by increasing powers of 2 because that's what our x of n is. Now, if you observe this is essentially a sum of finite geometric series. So you use your power series formula, and I'll talk about that in just a minute, and you can write the sum of the geometric series as this. And you can simplify it a little bit further. And if you notice, this cannot be so ROC over here is going to be everything in the complex plane, and because you are seeing a lot of negative powers of z, you're going to have to subtract 0 from the region of convergence. Now the question is, how did I go from here to here? And from here, the last step is sort of pretty straightforward, but this to this is actually being done by using the formula to compute the sum of geometric series. You guys have seen this before, I believe, many times. Sum of geometric series. So if you have a series here, 1 r to so on up to r to the n, this guy has n plus 1 terms. In a compact manner, you can write that summation as 0 to cap n r to the n. You can write, this is what? This is finite geometric series, right? So finite number of elements here. So if you're doing a finite number of elements, then the formula is this: r raised to n plus 1 minus 1 divided by r plus 1. That's exact r minus 1. This is exactly what we used to write the result over here. Next, if x of n has a finite duration, exact the same way as we had earlier, then the sum in the Z transform will always converge except for all the complex numbers, but you have to subtract 0 and plus and minus infinity from it. Why do you need to subtract 0 and why do you need to subtract plus and minus infinity? Well, over here, because of negative powers of z, you have to subtract 0. And if this guy was also defined for time less than 0, then you would have had positive powers of z there. With positive powers of z, you would have to subtract plus and minus infinity from that ROC. So if it's a complex, sorry, if it's a finite duration sequence, the Z transform will be all of complex numbers, all of complex plane minus 0 and plus and minus infinity. 0 in general, but plus and minus, it depends on whether it is defined for n less than 0 and n greater than 0 or not. How can we relate this back to Laplace? When you had a finite duration signal in Laplace, what was your region of convergence? All of S plane. Exactly the same way as it appears over here. Next, what if you have an infinite geometric series? Well, the formula slightly changes. Here, we are using 0 to infinity, r to the n. It is going to be simple here, 1 divided by 1 minus r. Everybody remembers the famous one, right? 1 plus half plus 1/4. Yes? Okay. Right? What needs to be satisfied here? If you are summing up that geometric series, every time you're multiplying by half, right? So you got a 1 from there, and everything else gave you a 1, almost. So you got 2, which is 1 over 1 minus r. 1 divided by 1 minus half gives you a 2. What has to be valid for this? This has to be half, right? But it has to be less than 1. So every time you multiply, this will converge to a value only when the magnitude of that r, because it could be complex, magnitude of that r has to be less than 1. Even if it is 1, then it will take you to infinity, right? Because then you're doing 1 plus 1 plus 1 plus 1 and so on. The magnitude of that has to be less than 1 for it to converge. So using this, our ROC for Z transform is going to be defined based on this. Magnitude of r has to be less than 1. So if I go back here, take a look at this formula. X of n, z to the minus n. If I'm able to express this guy as something raised to the power of n, then all I will need is that thing, the magnitude of that thing, to be less than 1. That will define my region of convergence. Can you see that? Let's go back, and we have talked about this. Yes, we have talked about this. Right. So if it is infinite length, then the summation becomes infinite sum. It might not converge for certain values of z. For example, this. Depending on whether the magnitude of r is less than 1 or not, that would define your region of convergence. And we'll do some examples over here. Questions so far? Simple use of sum of geometric series. Finite case, infinite case. Calculate the Z transform of a step sequence u of n over here. This is a right-sided sequence. If it was a Laplace and you were doing u of t, what would you get? Anybody remember u of t? What do you get for Laplace transform? What is that? 1 over s. 1 over s tells you that there is a pole at origin. There's a pole at origin, and because it's a right-sided signal, the ROC would be to the right of that pole, right? It is right of the pole. This is j omega axis. This is your x-axis. The ROC is where? Here, right? When I close it, where does this become? It becomes to the outside of that circle. You guys see that? So that's how I want you to relate Laplace and Z. Now, let's go and take a look at the math here. I need x of z. I'm given x of n. X of n is simply 1 from 0 to infinity. It's a right-sided sequence. U of n is only defined between 0 and infinity. So I'm going to reduce this down to 0 here. And for all those times between 0 and infinity, u of n is simply 1. I've got a very nice geometric series now, right? All I would need is this guy. So I need to express it as r to the n. What is that? I can express this as z to the negative 1 raised to n, right? So that's my r to the n. And if this is an infinite geometric series that needs to converge, it will converge if magnitude of r is less than 1, right? Which is written up right here. Can I see that? And you can rearrange it to write that as magnitude of z should be greater than 1. But if magnitude of z is greater than 1, what does it converge to? Well, 1 divided by 1 minus r, depending on, based on the formula. So you know what r is, z to the negative 1, plug it in there, simplify, you will see z divided by z minus 1. Now, another key thing that I want you guys to notice is this. When you saw the Laplace transform of signals in the form of u of n, or sorry, Laplace u of t or e to the at u of t, what did you see in Laplace domain? You saw 1 divided by s minus a, right? But over here you are seeing z divided by z minus 1. So notice that difference, that in the numerator you have a z term, right? That will be a difference consistently across the board that you will have to look for. Z in the numerator. Why is this important? When you go and start doing partial fractions, you will have to save that z term. Because earlier you just did partial fractions and you got 1 divided by s minus a, or k1 divided by s minus a, k2 divided by s minus b, and so on. Your numerator didn't have an s. So partial fractions went without that s in the numerator. Now when you do partial fractions, you will have to save a z term in the numerator. In other words, if you don't have a z term in the numerator, you will have to manipulate it to such like z to the negative 1, multiply and divide by z. You will have to force a z term onto it, because only for those things we have a time sequence that is defined. For example, u of n in this case. The other thing that I want to point out is, when you look for Laplace transforms, you will only see s's, right? You will see a polynomial in the numerator, you will see a polynomial in the denominator. When you start seeing z's, z transform, you will often see it being expressed in negative powers of z, just as you have here, 1 divided by 1 minus z inverse. That's of course optional. You can also express it like this. But what I want to point out is this is also something that you will see very often. Now, what does this have? This has a 0 at 0, and there's a pole at 1. So let me just put that up here. I've got a 0 at 0 and a pole at 1. And the pole is actually defining my boundary for the region of convergence. Because depending on my infinite geometric series getting converged, I said the region of convergence is all of complex plane with the distance away from origin to be greater than 1. Right? Magnitude of z has to be greater than 1. So everything outside this unit circle is going to be my region of convergence. So j omega axis essentially collapsed, right? Let me just draw here. This is sigma, this is j omega. This guy actually collapsed like this and became a circle, right? So earlier, you had a pole there, and the region of convergence was here. When it collapsed like this, the region of convergence became to the outside of that unit circle. So G omega axis collapsed into a unit circle. Right here. So R is 0, right? So region 0 is at 0 because of this guy. Yeah, but our pole. So this pole is because in Z domain you have a pole at 1. This pole is because in our Laplace domain you had a 1 over S. So for U of t, you didn't have a 0, you just had a pole. For U of n, you have a 0 and you have a pole. Pole is what is dictating whether, what is the boundary of that ROC. Now, with this discussion, can you guys tell me the 4 possibilities here? So here, you said right-sided signal, left-sided signal, two-sided signal, finite duration, right? Okay. What is the ROC in Laplace? Left of the leftmost plane, right of the rightmost plane, a vertical strip, or everywhere. What would it be for Z transform? Outside of a circle, inside of a circle, everywhere, right? Or what is the last one? A ring, right? Like a vertical strip would now correspond to a ring. So those are your 4 possibilities. Inside circle, outside circle, ring, everywhere. And then you will have to subtract the 0 and plus and minus infinity appropriately for a given signal. All right, let's move on here. Next, we are calculating the Z transform of a sequence a to the n u of n. A belongs to a set of complex numbers. So you have a complex number raised to n u of n. Again, plug it into the formula. U of n is present, so it will help us simplify the limits of the summation from 0 to infinity. Now, what are you going to do? You're going to take this guy over here and try to represent this as some raised to n, right? So you will say a z -1 raised to n, right? Yeah, and then this will converge when R, magnitude of R is less than 1. So magnitude of a z -1 is less than 1, right? Can you see that? What does that imply? That implies that, let's see, magnitude of z inverse has to be less than 1 over magnitude of a. In other words, you can say magnitude of z has to be greater than magnitude of a. So go from here to here to here to here to get your region of convergence. What does it converge to? 1 divided by 1 minus r. 1 divided by 1 minus a z inverse. Z to the -1. Instead of saying z inverse, I should say z to the -1. Because z inverse means something else, right? Z inverse means coming from z domain to time domain. So you can leave it as like this, or you can simplify it to have z divided by z minus a. Again, you see that z term in the numerator that needs to be saved while doing partial fractions. Now, do it on a pole 0 plot and try to sketch the ROC. Here, because we are using a, and a is any complex number, it can be anywhere. So I'll just pick this as that particular pole, right? So this is that pole. Where is the pole? Pole is at a. There is a 0 at 0, and there is a pole at a, and I'm using this as that a location, complex location. The distance from this origin to that is going to be magnitude of a. And the ROC is going to be sketched such that all the complex numbers that are beyond that pole, so outside of that circle, whose distance away from origin is magnitude of a. That's going to define your region of convergence. So when you had unit step sequence, it was unit circle. When you had a to the n u of n, you had a circle with a as your distance, magnitude of a as the distance, because a can be complex. So we need to talk about magnitude of a. Questions about this example? Pretty straightforward. All right. What about a left-sided sequence? Over here, you have negative u of -1 minus n. How do you deal with that? Well, try to do the same thing. X of z, formula of the z transform. There is a unit step over there, so that will help us define the limits on that summation. This is u of -1 minus n. So we are looking for what? We are looking for non-zero values when -1, -n is greater than or equal to 0, right? Only then it will have non-zero values. In this case, it will have a value of -1. So if you use that, you will see that n goes from -infinity to -1. All of those times, x of n is simply -1. So you have a negative sign to take care of. This, when you expand it out as a sequence, you will see that it is negative z plus z squared plus and so on, an infinite series. Now, you can use your results from sum of infinite geometric series. What is that? Here, it's not starting from 1, right? So you can add and subtract a 1 there, but you will have negative z divided by 1 minus z, or you can represent it as simply z divided by z minus 1. For it to converge, you needed magnitude of z to be less than 1. So here you have got a left-sided sequence, and the region of convergence is now going to be inside of that unit circle, right? Earlier, left-sided sequence was on the left half of the plane. Now, did you collapse it? It became inside the unit circle. So for a left-sided sequence, or for a left-sided x of n, it has the same z transform as u of n, z divided by z minus 1. The only thing that is changed is the ROC became inside of that unit circle. We still have a 0 at 0. I have a pole at z equals 1. Questions about this? Right-sided sequence, you know where the ROC is going to be. Left-sided sequence, you know what the ROC is going to be. Now you can sort of go beyond this, right? You can say, okay, what about if I'm using linearity? This plus this. Well, find the Laplace z transform of this, z transform of this. The region of convergence is going to be the intersection of this and this. So, circle and then circle and intersection, you get a ring. Okay, let's move on here. The properties of Z transform. Linearity property. What is very similar to what the properties that you have been seeing so far. In fact, identical to the one in Laplace with region of convergence conversation. X1 of n, the Z transform is cap X1 of Z, region of convergence is R1. X2 of n, Z transform is X2 of Z, region of convergence is R2. If you have a sequence in time, discrete time, as AX1 plus BX2, its Z transform will be AX1 of Z plus BX2 of Z, and the region of convergence can be evaluated by finding the intersection of the individual regions of convergences. R1 intersection with R2. A and B over here belong to set of complex numbers. They can be anything. So linearity property, you guys have been seeing linearity property since convolution. Go ahead. No. We have done more than enough proofs for the semester. Yeah, no, you don't have to worry about that. Let's try to calculate the Z transform of this particular signal. Let's observe this signal a little bit. Here you have a cosine omega naught n and u of n. Now u of n I can handle. How is that? Well, when I apply that summation, u of n will help me define the limits to that summation, only greater than or equal to 0. How do I deal with cosine omega n? I need to express it in some power of n, as a power of n. I will use Euler's, right? So if I use Euler's identity, I can write cosine omega naught n as half e to the j omega naught n plus half e to the minus j omega naught n. So I'm rewriting the signal as two pieces of the complex exponential. Both are getting multiplied by u of n from the original signal. Now I can go into the math. I actually don't even need to go into the math, right? I have already done it. This is already in the form of a to the n u of n. and this is a to the minus n u of n, where a is any complex number, so the complex number over here is e to the j omega naught n. So because I've already done this before, right? A right here, a to the n u of n. What is that? Z divided by z minus a. So if I go back, so you got half from here, z divided by z minus a. And then for the other guy, you've got half over here, z divided by z minus a. Yeah. And then the magnitude of these guys is always 1, right? So we are looking at magnitude of z greater than 1. Notice also here, the signal is right-sided. So when the signal is right-sided, you are going to get an ROC that is going to be beyond the pole, right? Outside of the circle bounded by the pole. And the pole is what? The pole is on a unit circle. Somewhere in the unit circle, I don't know where, because I don't know omega n and n. Somewhere on the unit circle, there is a pole. Outside of that, magnitude of z greater than 1, that's going to be my region of convergence. Questions about this? And from here, you can simplify it to express it in this form. And that form is what you see on your z tables. So far, it's plug and chug, right? Plug it into the formula, use the sum of geometric series to find the result, as well as to define the ROC. Next, let's do it for a slightly different one. Here you have got your sequence x of n as 2 to the n u of n minus 4 3 to the n u of n. Again, we'll use the same result here. A to the n u of n, the z transform is z divided by z minus a. Same one as we derived earlier. So for 2 to the n u of n, you have got z divided by z minus 2 outside of the pole limited at 2, right? So outside of the circle whose radius is 2. Over here, 3n u of n, z divided by z minus 3 outside of the circle that is that has a radius of 3. Now, when you put these two guys together, this minus this, so z transform should be this minus this, multiplied by 3 and 4, of course. So you've got 3 times the first guy minus 4 times the second guy. And the region of convergence is going to be the intersection. So what is the intersection of these two guys? One is beyond 2, one is beyond 3. What is it here? Let me draw one. And I think I can draw it with this. It's funny. All right, so I've got the 2 and the 3, right? So outside the red guy, outside the blue guy, the intersection is going to be only outside the blue guy, right? So magnitude of z greater than 3 is going to be your ROC. So everything outside this. So what does the statement become? The statement earlier was for Laplace was what? My ROC is for a right-sided signal, my ROC is to the right of the rightmost pole. What does it become here? My ROC is going to be to the outside of the outermost circle, right? The biggest radius circle here. For right-sided signals. For left-sided one, it will be inside the innermost circle. And for finite duration, then we are talking about everywhere. Two-sided signal, then we are talking about a ring. Here, time shifting property. What happens to the Z transform when you do a time shift on the discrete sequence? ROC x of n, Z transform is x of z, ROC is R1. When you shift signal x by n0, then you multiply by z to the negative n0 in the Laplace domain. Region of convergence is R2, but R2 is the same as R1 minus 0 when there is a delay, meaning n0 is greater than 0, or R2 is equal to R1 minus plus and minus infinity if n0 is less than 0, which is corresponding to an advance. Now, can we maybe quickly validate these statements? Let me try to do this. If I go back and take a look at this example here, the 2 to the n example, there. If I shifted this sequence left, I'm advancing it. If I advance this signal, then I will start seeing n to the negative, n being negative, right? If I move this sequence left, x of n, if I move it left, that means I'm going for x of n plus 1 here. I'm advancing the signal. If I advance the signal, what do I have for n? I have n minus 1, n equals minus 1 defined, n equals negative 2 defined. What does that translate to in x of z? Positive powers of z. When you have positive powers of z, then you have to remove plus and minus infinity from it. You see that? So advance the signal, subtract plus and minus infinity for advance. Advance the signal, remove plus and minus infinity for advance. Can I see that? And then, of course, if you go this way, then you are having z to the negative powers, you're delaying the signal, and you're subtracting 0 from it. Go ahead. Absolutely. So only when it is appropriate for the signal, only then you would need to do it. You're absolutely right. Other questions? All right. Let's do another example. Here we have a finite duration sequence. X of n is 1 between 0 and 10, and then it is 0 everywhere else. We first represent that using step sequences, u of n minus u of n minus 11. Remember, u of n minus, it doesn't stop at 10 like continuous. Stops at 11 because at 10 you have to subtract that element out. Next, u of n minus u of n minus 11. For this, I've got the z transform. U of n, the z transform is z divided by z minus 1, and the ROC is outside of the unit circle, z greater than 1. The other piece, u of n minus 11, that is simply z transform of u of n with a time shift of 11 time units. So that would give you z transform of u of n, z divided by z minus 1, multiplied by z to the negative 11. You can leave that as is. Over here, the ROC is still magnitude of z greater than 1. Now, notice over here, we didn't subtract a 0, right? Because it was already not there. It was already not there in the original one. Magnitude of z greater than 1, 0 is already not there. So why talk about it? So here, the region of convergence is going to be magnitude of z greater than 1 outside of the unit circle. But if you simplify this guy down, you will get this, z to the 11 minus 1 divided by z to the 11 minus z to the 10. Questions here? Using Laplace transform, z transform of u of n along with the time shifting property. And also the fact that we are using linearity. And go ahead, Billy. Previous one. So if I go back, right, take a look at this example. Suppose I have this x of n. If I were to advance it, meaning I'm moving it left, right? If I move it left, you are going to, instead of this being defined from 0 to 10, it will be now defined from negative 1 to 9. But it will have a negative value in n. So when I apply x of z formula for computing the z transform, the first term that you will see is 2 raised to negative 1 z to the positive 1, right? Because you see x of n multiplied by z to the minus n. So z to the first element was at negative 1. So when you do a z for the first element, you are going to get z to the negative of negative 1, z to the positive 1. That will mean that the first term over here, when you move it left, is going to be having a z. and it has to converge. If z is plus infinity or minus infinity, it cannot converge. So I have to remove that from the set of complex numbers. See that? So if I'm moving it left, the moment I get negative values of n for which the signal is defined, I will start seeing positive powers of z in the z domain. So I have to remove the plus and minus infinity for those cases. Right. So everything, but it cannot include plus and minus infinity. All right, let's keep going here. Where we? Okay, so here, right? Yeah. So this particular problem involved the use of time shifting property, linearity property. Yeah, that's it. Those two. And the standard Laplace transform for u of n. That's it. Those are the three things that we used here. Okay. This is where I wanted to get to. Now you have the problem set up as find the inverse z transform of x of z, a rational x of z. You have a polynomial in the numerator, you have a polynomial in the denominator. How do you deal with this? The answer is quite simple. You deal with it exactly the same way as you did with a rational Laplace transform. The difference is instead of s's, now you have z's. Another difference is earlier you were breaking it up such that you get 1 divided by s minus a. A is some complex number, but you are breaking it up to get k1 divided by s minus a, s minus b, s minus c, and so on. Because for those factors, after you do the partial fraction expansion, for those guys, you could directly say this is e to the minus at u of t, right? You had the result ready for that. But now, when you do the partial fraction expansion for the z transform, you are going to have to save a z term in the numerator. That's the only difference. Everything else is going to be the same. Yeah? Let's do that for this particular example. So we had the polynomial in the numerator, polynomial in the denominator. We save a z term. How do we save a z term? We bring it out, leave one of the z's in there. You have the denominator factored out. Now for this, you have the order of the polynomial in the numerator is 1. Order of the polynomial in the denominator is 2. You can use your standard partial fraction results to break it up as k1 divided by z minus 1, k2 divided by z minus half. Do the partial fraction expansion, find out the residues. You will see k1 and k2 come out to be 2 and negative 1. Plug those values in there. You will get x of z as z times this guy plus minus this guy, right? So save the z term. Whatever remains, do the partial fraction expansion for that. Now you are in this particular form for which we already know the inverse z. 2 times, what is this? 2z divided by z minus 1. What is that? 2 times u of n. And then for this guy, what do you have? Minus 1 times half to the n u of n. This is z divided by z minus a. So I'm using this, right? I'm using this property here. A to the n u of n, the z transform is z divided by z minus a. And if this is a right-sided sequence, then magnitude of a has to be greater than 1. No. Magnitude of z has to be greater than magnitude of a outside of that circle bounded by a. That's your ROC. So that's what I'm using here and here. You guys see that? Z transform, find the inverse, save the z term. Everything else is following the same technique as Laplace. Next. Oh, we did this already. Oh, no. This is with some other x of z. In this x of z, there is no z term. You see, or at the beginning here, x of z is given. We need to find x of n, but there is no z in the numerator here. So what will we do? We will try to force it. This z, I can bring it over here. Why am I doing that? Why am I bringing a z as a product in the numerator? Because I know that that is direct application of time shift property. I can have z to the negative ones in the numerator and directly apply time shift property at the end. Now, I needed another z in my numerator. So in order to get a z in the numerator, I multiplied that. And to compensate for that, I multiplied a z inverse. Now, if I combine these two guys at a later stage, I can use time shifting property, right? And I can use this guy as the saved z term. You see that? And then I will use the same thing. So I've got z to the minus 2, and then I've got the saved z term here. These guys need to be dealt with using partial fraction expansion. I have k1 divided by that, k2 divided by that, use partial fraction expansion, find the residues, plug it in there. You have got z to the negative 2 multiplied by this term, and they both have z. So the z term that you saved here is being used up here and here. Z to the negative 2 term remains as is over here and as is over here. Now, this and this, they are already in the standard form, right? So you can say the inverse Z transform for these two guys here and here is simply going to be 1/3 2 raised to n u of n minus 1/3 negative 1 raised to n u of n. Once you have done it for everything without the z minus 2, you can apply the time shifting all the way at the end, where you are taking all the n's and replacing with n minus 2s. N minus 2, n minus 2, n minus 2, n minus 2, and you're done. Questions here? So, any rational z transform that is thrown at you, remember to save the z term in the numerator. And if you are seeing any negative z terms, just bring them up and deal with them using the time shift property. Questions? All right, next property that we are looking at is a time reversal property. If you flip the signal in the time domain, the z transform of the signal will now be the same function, but all the z's will be replaced with z inverse. Right? You just need to take all the z's and then substitute z inverse for that. That's it. How about the region of convergence? Well, if the region of convergence was, say, outside of the unit circle, now it will be inside of the unit circle. Right? It will just flip. So the inverted ROC. Proof is over here. X of n. Well, I'm not going to do the proof. Let's just save time there. All you need to do is replace or substitute z to the negative 1 instead of the z's. And that's how you do the time flip. Let's actually apply that for an example. I think that's a better investment of our time. So we have an example here, a to the n u of n. The z transform of that is z divided by z minus a. The ROC of that is magnitude of z should be greater than magnitude of a. Over here, a is belonging to set of complex numbers. What is the z transform of a to the minus n u of n? Well, that's quite simple. We just take x and substitute z to the negative 1. What is that going to be? Well, it will be z to the negative 1 divided by z to the negative 1 minus a. And what would be the ROC? ROC will be magnitude of 1 over z is greater than magnitude of a. So this will simplify to what? You have a 1 over z, 1 over z. So 1 divided by 1 minus az. Is that right? And then over here you will have magnitude of z less than magnitude of a. Is that okay? No. I can't write this. I just need to flip the region of convergence. So I need to write this for both of them. Z was greater than a. Now ROC gets inverted. Z has to be less than a. So inside of the circle, outside of the circle. Any circle with that distance a away from it, magnitude of a away from origin. Time shifting just involves replacing all the z's with z inverse and inverting the ROC. Good. No, we don't. For this one, we don't. If we were doing one more step beyond this, right? Suppose I was taking this and trying to find the inverse z transform with something like this, then I would need a z term there. But if you're going to deal with something like this, when you go to the inverse, you are going to need to go to a to the minus n u of minus n. So sure, you don't need the z term as long as you know that the property refers to a to the minus n u of minus n. If you have that z term in the numerator, it will take you to something that is right-sided, a to the n u of n. But because of that manipulation that you did, you will eventually do the time reversal anyway. Next, what happens when you differentiate in the time domain? In the z domain. The z transform pair is given over here, x of n, z transform is x of z, ROC is some region R. If you differentiate in the z domain and you multiply by negative z, in the time domain you are multiplying by n. N x of n, the z transform for that is negative z derivative of x of z with respect to z, ROC doesn't change. So again, the proof is provided over here. Let us quickly run through the proof. And this is not the proof. This is an example. N a of n u of n. That is a signal in time domain has an n that is getting multiplied with something that we know the result for. So we are going to use the known transform z transform here, which is a to the n u of n. Z transform is z divided by z minus a. ROC is defined by magnitude of z greater than magnitude of a. Next, if I'm multiplying by n in my time domain, what is happening in the z domain? In the z domain, you are multiplying by negative z, but you're also differentiating the function in z domain with respect to z once. So differentiate the function with respect to z, but also multiply by negative z. So you have the negative z term, differentiate with respect to z, simplify, ROC doesn't change. So if you start seeing n in your time domain, multiplication by n, then you know that you are going to have a derivative in the z. Now, the more n's you have in the time domain, n squared and cubed, those many number of times you will have to multiply by z and differentiate with respect to z in the z domain. Again, property is listed in the z tables. Convolution property. So what is this? This is if you are convolving in the time domain, you are multiplying in the frequency domain. What are you multiplying with what? You are when you were doing Laplace, you are multiplying the Laplace transform of the input with the transfer function, right? The transfer function was obtained how? You obtain the transfer function by evaluating the Laplace transform of the impulse response. We're going to do the same thing over here. Y of n, the response of this discrete LTI system, can be obtained one way by convolving the discrete input with the discrete impulse response and running through the discrete convolution sum to do it. But in Z domain, you can also do this as a product. So if x of n has a D transform of x of z, the impulse response has a Z transform giving you the transfer function of the discrete LTI system as cap h of z, then the output, Z transform of the output is going to be simply the product of x of z and h of z. So time convolution, product in Fourier transform, Laplace domain, even in Z. Over here, I'm listing out the steps that are involved to prove this property. Not going to spend time there. How do you deal with repeated roots? You have x of z given to us as z squared divided by z minus a whole squared. So you've got two zeros at 0 and you've got two poles at a. What is x of n? Well, we can do a lot of things with this. You can save a z term, you do partial fractions, then you can go through that standard approach, or you can notice that this is product of two functions that are exactly the same, z divided by z minus a multiplied by z divided by z minus a. So you can treat this as you're multiplying in the z domain, so you must be convolving in the time domain. So what you can do is inverse z of this guy is going to give you a to the n u of n. Same thing applies here. So x of n is literally the self-convolution of a to the n u of n, right? Convolving both of them together. How can we deal with this? Well, run it through the convolution sum. Because of the presence of u of n, you can quickly simplify your limits of the summation. You don't need to go from negative infinity to infinity. In fact, you only need to go from 0 to n, and within that you will have a to the n. So a to the n, now it's a finite geometric series. No, it's not even a geometric series. You're summing up with respect to k, and you have a to the n. So you're literally adding up n plus 1 times a to the n. So it's n plus 1 times a to the n. If n is greater than or equal to 0, it is going to be 0 otherwise. Combining these two statements, you can write x of n as n plus 1 times a to the n u of n. All of this to say this. This is obtained, a simple way of, this is obtained by convolving these two. That's it. And those two, the convolution of those two signals, we have done a lot with such things when we were talking about discrete convolution. And this is what approach? This is not the graphical approach. This is not the, which approach is this? Analytical approach, right? So analytical, whenever you're seeing u of n's and some sequences that are going on forever, you don't want to do graphical. You want to do analytical. All right, let's move on. Talking about discrete time LTI systems, their response of LTI systems maps exactly the same as response of LTI systems with the conversation of Laplace. X of n, discrete input. H of n, discrete impulse response. H of z, transfer function of the discrete LTI system. Output sequence y of n, obtained by doing discrete convolution of the input and the impulse response, or z transform of the output, product of the z transform of input and the transfer function. Now consider, essentially this slide is going to prove where does the z transform come from. Now, just as a refresher, I will use LTI system and I will use h of t as my impulse response, and I have h of s as the Laplace transform of h of t. You guys remember what did we have for this? Say if the input is e to the st, what did we have for the output? That, right? E to the st h of s. So this was the eigenfunction, right? And this was the eigenvalue for LTI systems. We are going to use the same conversation. We are going to try to map it to our discrete LTI systems. Over here, consider the special input. Like we did e to the st, now for z, consider z to the n. So if z to the n goes in, and you have a known impulse response and a known h of z, what is going to be the output? The output is simply obtained by convolving the input and the impulse response. The input is z to the n, the impulse response is a to the h of n, and I can express that using the discrete convolution sum. H of k is z to the negative z to the n minus k. And I'm summing up with respect to k, so I can bring all the n terms outside. Like this, z to the n is brought outside, and I'm left with something that depends on h. That's it, right? Z to the negative k is just some values of z that are getting summed over, negative infinity to infinity. So I'm going to define this as my input, and all of this as my h of z, right? E, E, H. The LTI system has eigenfunctions of e to the st, their eigenvalues are h of s. For z transform, z to the n is your eigenfunction with h of z defined as the z transform is as your eigenvalues. And you can see h of z is defined as this, right? H of k is e to the minus k. That's exactly what our z transform was based on. So that's sort of the derivation of z transform. All right. Can I use that to solve this particular problem? I have an input, a discrete sequence x of n. It has some cosine term. So Euler's identities are ringing in my head. There's a r to the n, so that's good. U of n is going to help me limit the summation. So all of that is good. My LTI impulse response is given, so this is known here. And I need to find y of n. And I'm going to do that exactly this way, right? Y of n is z to the n multiplied by h evaluated at those z's, right? So the first thing I'll do, use Euler's to break the cosine into two complex exponentials. Next, I will isolate these terms. I've got r to the n half e to the j n omega naught u of n. All of that goes here. And then whatever remains, which is r to the n half e to the minus j n omega naught u of n, all of that goes over here. Now they are in standard forms. What is that? Half a to the n u of n, half a to the n u of n. Now, if you consider z as r e to the plus or minus j omega naught, what do you have? Half r to the n u of n plus half r to the n minus n u of n. You can now use the eigenfunction and eigenvalue conversation that we had for these kind of special inputs. The output is simply going to be half from here and half from here. Where's the other half? Let me just draw this. This half is coming from there. That half is coming from there. Next, you multiply with z to the n. All right. What is z? Z is r e to the plus or minus j omega. But here it is plus, here it is minus. The input is z to the n. The output is going to be z to the n multiplied by h of z. Z to the n, h of z. Next, for this guy, half carries over. The input is z to the n. Output is what? Z to the n, h of z. Z to the n, h evaluated at this particular z. That's it. That's your. So you didn't need to go into Laplace domain. You just evaluated it directly. For what kind of things you can do this? Well, if you have some signal over here raised to n, for those z, some complex number raised to n, you can apply that. All right, next, couple of things quickly. Conjugate property, x of n, if the z transform is x of z, that is known, region of convergence is R. Then if you take the complex conjugate of the signal in time domain, then in the z domain, you replace all the z's with z complex conjugate, but also the function x of z gets complex conjugated. The region of convergence doesn't change. How about time differentiation? This is the first difference property. If x of n goes to x of z in the z domain, region of convergence is R. The difference between the first x of n and x of n minus 1, the difference between them, which is essentially sequence minus delayed by 1 second, same sequence, is x of z minus z to the negative 1 x of z. This is where you can simply prove that using the time shift property and linearity property. You can prove that. That's also called as the first difference property. The region of convergence is going to be at least be 0 while you intersect with z magnitude of z greater than 0, because there is a negative 1 over there. 0 and negative 1 over there. So you have to remove the 0. Let's move on to accumulation. If x of n has a Z transform of X of Z with some region of convergence R. If you sum up all the elements in X of N, sum up all the elements, then the resulting Z transform of that is simply going to be 1 divided by 1 minus Z inverse. X of Z remains as is. And in this case, region of convergence is going to be at least R intersecting with magnitude of Z greater than 1. So that is, this guy is coming from this, and that is because of that the elements in X of N getting accumulated. So adding up all the elements in X of N results in multiplying 1 divided by 1 minus Z, or simply Z divided by 1 minus Z. Z divided by Z minus 1 in the Z domain. Next, initial value theorem. If X of N is 0 for time less than 0, then what you can say about the first element of X of N is that it is going to be limit Z tends to infinity X of Z. Take the Z transform, evaluate the limit of Z tending to infinity. That's how you will get X of 0. Next, stability. Let me just take a couple of minutes here about this, and then we'll stop. If I know this particular Z transform, which is a to the n u of n, the Z transform of that is Z divided by Z minus a, and a is any complex number, then there are several possibilities. A could be real, A could be complex and its magnitude could be greater than 1. A could be complex and its magnitude could be less than 1. A could simply be complex, no limitation on the magnitude, and magnitude of A could be exactly 1. What is going to happen to the stability when A is one of these criteria? So let's take a look. A belongs to the set of real numbers. When that is the case, what do you have? 2 to the n u of n, 3 to the n u of n. Your response is exponential, purely exponential. There are no oscillating things. It is purely exponential. Because all you're doing for those things is what? R to the n goes in, or Z to the n goes in. What do you get? Z to the n, H of Z. Right? There's no oscillatory behavior. The behavior is purely exponential. But if you have A to be complex, then you could have magnitude of A greater than 1 or less than 1. If magnitude of A is greater than 1, what do you have? 2 raised to n, 3 raised to n, 4 raised to n. Right? So things are exploding. It's unstable as time goes on. But if magnitude of A is less than 1, then things are decaying as time goes on. They are converging. It is oscillatory because A is complex. It is giving you some omega naught, right? Some frequency, some oscillatory behavior. Right? A of n, U of n, like some complex number to the raised to n. It's going to have, using Euler's identity, you can have a cosine part and a sine part. Some oscillations will be there. But if magnitude of A is greater than 1, those oscillations are sort of growing with time, exploding. When magnitude of A is less than 1, then those oscillations are decaying down. If A is complex, generally, if we don't know the criteria for the magnitude, at least we know that it is going to keep oscillating. If magnitude of A is greater than 1, is exactly equal to 1, then we know that even magnitude of A to the n is also going to 1. So you can use that when you evaluate the eigenfunction and eigenvalues using Z to the n goes in, Z to the n, H of Z comes out. So if you sketch this on like on a plane, on a Z plane, you have a real part of Z on the x-axis, imaginary part of Z on the y-axis. You have the unit circle over here. If you are on the real axis, A could be greater than or equal to 1. Magnitude of A could be greater than or equal to 1, or it could be more, right? So you could be inside this on the real axis, or you could be outside this on the real axis. When you are inside this, you have a stable exponential. You're going down with time. When you are outside this, you have an unstable exponential. No oscillations, but exponential that is growing. If you are outside of the real axis, you will have oscillations. A is complex. You could be inside the unit circle, magnitude of A less than 1. You could be outside the unit circle, magnitude of A greater than 1. Oscillations here, oscillations here. Inside the circle, stable oscillations. Outside the circle, unstable oscillations. Oscillations growing, oscillations decaying. What is the, we said oscillations, so let's talk about what is the frequency of those oscillations. Now, if A is that complex number, A to the n u of n, A is complex, right? So if it is complex, I can write that as magnitude of A e to the j angle of A. That particular complex number can be written or broken down in using Euler's as some real part, some imaginary part. The real part is going to be, what is that? Magnitude of A raised to n, cosine theta A, and then imaginary will have sine component. They will have some frequency. What is that? Theta A will determine the frequency of the oscillation. So depending on the complex number A that you have, if it is complex, that will define the frequency of the oscillations. They could be stable or it could be unstable, depending on whether they are inside the unit circle or outside the unit circle. Okay. That is all I have for you guys. I will stop with this discussion here. Stop recording here as well.